PG polymer composites. Now I request Dr. Raghavendra Gujala Garu proceed further with the presentation. Thank you, sir. Over to Raghavendra Gujala Garu.
Thank you, ma'am. Good afternoon, everyone. Let me share my screen. Is the screen visible?
Yes, sir, visible.
Yeah, thank you. Thank you, ma'am, for the introduction. I'm Dr. Raghavendra. So my research areas are composite materials and nanomaterials. So today's topic is about nanomaterials. Broadly, I have given an area like nanomaterials. I came to know that earlier speakers also had discussion, given lectures on same nanocomposites. So due to that, I'll start my presentation with materials and what are the different type of composites which we can fabricate. And after that, nanomaterials, how the nanomaterials will be prepared, what are the different techniques to fabricate nanomaterials, and what are the different type of nanocomposites which we can prepare, and what are the calculations required when we are fabricating that composites, and a little bit related to the characterization of that nanocomposites. So coming to the first slide, the first, as I said, like we'll start with classification of materials. So coming to the classification of materials, so in this picture, I have given a classification which is related to two terms. One is natural materials and man-made materials. But when we start with the classification of materials, we start with this picture, like engineering materials. So we'll start discussing like metals, non-metals. So in the metals, we have ferrous, non-ferrous, and then plastics, which is related to the non-metals, plastics, ceramics, composites, all this. But the basic classification starts with natural materials and man-made materials. So the materials which are available in the nature, that we all called as natural materials. So the metals, polymers, ceramics, and alloys, all these materials are man-made materials. So they are not available straight away in the nature. So here, if you see natural materials, examples like stones, skins, bones, mud material, and wood materials. So all these materials are natural materials. So on the other side, like man-made materials, like some materials which are available in the nature, man modified those materials. Like for example, let us take metals. Those metals are not directly available. They are available in terms of ores. Those ores will refine it and then we'll modify it to different metals. And we can prepare different type of alloys. Again, polymers right away in the nature, they are not available. We'll fabricate those polymers like plastics, thermosets, and elastomers, and ceramics, and different type of ceramic materials. So the first classification starts with natural and man-made materials. Again, engineering materials. In the engineering materials, these are all man-made materials. So for example, like metals, in this we have ferrous and non-ferrous, amorphous. Again, there is a sub-classification. So the topic is not about engineering materials, so I'm not going deep into it. Coming to the plastics, there are thermoplastics and thermosets and elastomers. So there are three classification in the plastics. Again, there are thermoplastics, their properties are different. Thermosets, their properties are different. Elastomers, their properties, structures are different. Coming to the ceramics, these are high temperature resistant materials. In the ceramics, we have different type of ceramic materials. As you see in the screen, there are different type of oxides, nitrides, carbides. There are sub-classifications of ceramics. Coming to the composites. So the present day, like today's topic is about nano composites. So first we'll see what is a composite and we'll see what is nano composite. So composite, we'll have a reinforced plastic composite, metal matrix composites, ceramic matrix composites, and different type of laminates. So in the classification, we can name it as a microfiber composites, microfiller composites, nano composites, nanofiller composites. So first we'll see straight away directly to definition of a composite. Maybe already from the last 2 or 3 days, like when the this program started, many of the speakers already talk about the composite definition. You might have already familiar with this definition, and many of the people are working on this. So composite is a combination of 2 or more materials. Particularly in simple terms, we can say reinforcement plus matrix gives you composite. So in the picture, you can see some examples like mud straw bricks, concrete, glass fiber composites. The definition for composites and an alloy are same. So if you see like the combination of 2 or more metals, in an alloy also the combination of 2 or more metals. In the both the cases, the definitions are same. But in an alloy, when you combine these two materials, the base material lost their original structure, the base material lost their original properties, and the new formed material having a new properties, particularly in an alloy, when you combine 2 or more metals. But when you come to the composite, even when you combine 2 or more metals, their basic materials, which we are combining, they don't lose their original properties. They remain same, but they act as a single material, but their own properties remain same. So there is a basic difference between a composite and an alloy. So coming to the classification, like as I said, reinforcement and the matrix. So in this, we have a reinforcement and a matrix. So what is the use of reinforcement and what is the use of a matrix? Basically, matrix is a material which is used to surround the reinforcements. So this matrix material, it may be metal, polymer or ceramic. It is a continuous phase. It is used to surround the reinforcement. So when it is surrounding the reinforcement, it is not the load carrying materials. So matrix are the not a load carrying materials. It always, as it is surrounding the reinforcements, it always transfers the load. So these matrix materials always transfers the load to the reinforcements. So then the reinforcement is a material which carry the load, whether it may be continuous fibers or discontinuous fibers. When it is a particulate, again, the concept will be same, like load carrying materials will be the particles, but the majority of the load transformation as well as carrying will be taken by the matrix also in that condition, particularly when it is a particulates. So the matrix material is a load transferring material, reinforcement is a load carrying materials. So some classification related to matrix. We have a metal matrix composites, polymer matrix composites, and ceramic matrix composites. So when you are using these three as a matrix material, then we can call that as a matrix classification, like metal matrix, polymer matrix, and ceramic matrix. Again, in the polymers, thermoplastics and thermosets. In metals, we have a different type of metals. That metals we will use as a continuous fiber sometimes, sometimes use as a rod type of things, rod materials. So when you use as a metals as a rod materials, then we call as reinforcements. If you are using that metals as a continuous phase, then we call as a matrix material. So those are general composites. What is a hybrid composite? So I'm quickly like changing over from normal composites to hybrid composites, because the concept is about the nano composites. So we discuss more about nano composites. So I'm not discussing more about the continuous normal composites, continuous fiber composites, all those. So directly I'm going to the hybrid composites. So normal composites, when you are combining one reinforcement and one matrix, we'll call normal composites. When you are combining two type of reinforcements with one matrix material, that is called hybridization. So why we go for hybridization means, when sometimes, like let us take a glass fiber composite and a carbon fiber composite. So when I am combining these two materials, if I prepare separate glass fiber composites, individual glass fiber composites, individual carbon fiber composites, if you want to show for a particular application, if my application level, the strength of that particular application is, it's around in between the carbon fibers and glass fibers. Let us take glass fiber strength, individually it comes to 2000, carbon fiber strength is almost 5000. So if my applications are between that, between these two, between it is not 2000, it is not 5000, it is in between that, then if I select carbon fibers, the cost of the carbon fibers are higher. So the main concept for a composite is, less weight, high strength, low cost, high strength. So these are the two main parameters which we consider when you are selecting or designing a composite. So if I design a composite and I select a material like a carbon fiber materials, the cost of that carbon fiber materials are higher. Let us take 1 meter of a carbon fiber is almost 3,000. 1 meter of a glass fiber is almost 100 rupees. You can see the difference, how much it is, like 100 and 3,000. So if I use a glass fibers as a 4 layers, it costs me around 400. If I go for a carbon fibers or 4 layers, it costs me around 12,000. So if my application is such high in aerospace or some other, so that I can't compromise with the cost, then I go with directly with the carbon fibers, no other thoughts. If my applications is not so high, the cost of that application is not so high, then I need to compromise. So how to compromise? So directly I can't directly go to glass fiber because the strength of the glass fiber is only 2,000. The carbon fiber strength is 5,000. So I need a strength of 2,500 or 3,000. Then in that cases, I'll go for hybridization. So instead of using a 4 layers carbon fibers, I use 2 layers as a glass fibers and 2 layers as a carbon fibers. So in that case, the total cost of the composite is reduced and the strength is also not compromised, because the 2 carbon fibers increases the strength, and instead of getting a 2,000, I'll get more than 3,000 because the total strength of a carbon fiber is around 5,000. So mathematically also, if you calculate, it will be higher. So when we go for a hybridization, this is an advantage. Sometimes it is cost point of view side and strength point of view. Sometimes some properties, like for example, glass fiber having some tribological resistance will be in the glass fibers are less. In some cases, I need to increase the tribological resistance. Later, like we'll see the tribology also, like tribological, a little small introduction to tribology. So the wear properties. The wear properties of the glass fibers are less because these are synthetic glass fibers. When I impact with the different materials or sand or some other materials, automatically these glass synthetic materials having a less strength, less wear resistance. So when I want to increase that wear resistance of that glass fiber, so I need to go with any natural materials. So to increase or to substitute that property into the composite, I hybridize the material. So that is another concept, like to substitute some other properties, like once a material having some defects or disadvantages, that disadvantages will be rectified with some other material. So in that case also we go for hybridization. So hybridization means like combination, we can go for it. So that is called hybridized composites. In this, you can see it in the picture. So in the picture, you can clearly see that there are one bamboo mat, one glass fiber mat, and one bamboo, one glass fiber. So this is a hybridization, like natural fibers along with conventional materials. Sometimes like recently we have slogans like reduce plastic and remove plastic, remove the conventional materials which create pollutions. So when we are removing those things, again, we need to remove or replace those materials with the natural materials. Because if you see the cycle of the materials, we started with the natural materials. After then, the natural materials are replaced with metals. We have a metals. After metals, in 1940s and 1950s, we have a plastic. So the entire thing's now fully covered with plastics. All the metal materials, 90% will be covered or replaced with plastic materials and composites. Now we have a problem with these composites, with this plastics. Now we are thinking about replacing the plastic with the natural materials. Again, the cycle, like you can see, start from the nature, and again, we are going back to the nature. Nowadays, people are trying to develop new materials which are related to nature, biocompatible. So in that case, the only disadvantages with the natural materials are we are habituated to metals, which having a high strength. We are habituated to the lightweight materials, which is a plastics. And now again, we are going to the natural materials, which having a more defects. In a natural materials, there are more disadvantages, like there won't be a uniformity in the materials, and easily we can't replace these things. So to replace those things, again, straight away at one point directly, we can't replace the plastics. So step by step, we can replace it. We can reduce the usage of the plastics slowly. Later, we can clearly remove the usage of these plastics. So in that condition also, we can go for a hybridization. Instead of going for conventional glass fibers, we can try with the bamboo material or a jute material, natural materials, and we can see the strengths. how much amount of strength are coming to those materials, so that we can compare and we can replace those glass fibers in the applications, in present applications. So that is the idea behind this. So the other concept is, after hybridization, the concept which is nearer to nanotechnology, nanomaterials, are filler composites. Adding a fillers to the composites, whether directly adding a particles to the matrix or a metals or ceramics as a separate like a filler composite or hybrid filler composite. So two ways can be done. So some type of metal powders like aluminum, carbon, magnesium, and titanium dioxide, zirconium dioxide, all these pictures are taken from the online sources. So I didn't give the references to that. So these are the metal powders. So these metallic powders, it can be used directly as a fillers into composite, into the polymers or the metals, or these can be used as a fillers in hybrid composites, like one continuous fiber composites, to replace the gaps between the continuous fiber composites, and to reduce the matrix material. So we can add these type of filler materials. So in this particularly filler concept, we have two types of filler concepts. One is micro material, another one is a nano material. If we use a micro as a fillers, those composites are micro composites. If we use the same material in a nano level, then we call as a nano composites. So now we are going to nano composites. So we'll start our particular topic to this FDP. So our nano composites. So the definition itself tell you like a nano composites. Nano means, first we need to know what is a nano. Nano means mathematical terms, it is 10 to the power of minus 9. So if you see 10 to the power of minus 9, which is very small, which we can't see with our eyes, the least material which we can see with our eyes is almost 100 microns. That is our hair. The hair diameter only we can see it. That is the least size which we can see with our eyes. So that is 100 microns. If you see that is 100 microns, means nano means 10 to the power of minus 9, which is very small, which we can't see. Then what is a nano composite? Then people who don't know about the concept of composites and some other terms, automatically they will feel that like nano composites means which is invisible composites. It is nothing like invisible composites. So the definition gives you that in a continuous reinforcement in a matrix, if we use the reinforcement in a nano phase, then we call that as a nano composites. So the nano composites are visible. The particles which we are using in a nano level, then we call that as a nano composites. So whether it may be a fillers or continuous fibers, like the fibers may be used with the diameter level. Again, we'll see what is the different nano levels in the nanotechnology. In the next slides, we'll see that. So particularly in a reinforcement, if one phase is in a nano phase, then we call that as a nano composites. So now we'll see what is a nano. So simply mathematical term, if I say like 10 to the power of minus 9, simply to understand that, mathematically we can easily understand. But if you see how much small it is, if you start comparing that nano, then we can easily understand how much small it is. A small comparison to understand it clearly. A rough comparison. It's not a planned comparison. Like it is comparing with the largest star. Maybe these slides are prepared long back. I didn't update it. This is VV Chapai, which is a largest star in the universe. So you can see the value that is almost 26448, almost 5 zeros. That is the size of the kilometers diameter. This is the largest star. So that star compared with the sun, it is almost 1900 times bigger to the sun's diameter. Again, the sun's diameter is compared with the earth's diameter. The earth's diameter compared to the sun is 342 times. The sun is bigger than 342 times when compared to the earth's diameter. And suddenly like 1 meter child, like discussing the other things difficult. So 1 meter child height, again, you can see it 12756 times smaller meter. So now we'll see in this particular picture, now we can see we are entering into a microzone. Here in the microzone, you can see it, 1 penny a coin, it is a 2 centimeters. The raindrop is 1 mm. As I said, like the least particle which we can see with our eyes is a hair diameter, not a hair length, hair diameter, which is 100 microns. So the next one, 5 microns, blood cells. Those blood cells also we can see it, but an individual blood cell, we can't see it. It will be seen as a bulk. Okay. So the individual blood cell is 5 microns, that we can't say as an individual. We are seeing like as a bulk material. Okay. So this is a one thing. After that, now we are entering into the nano zone. We can see some materials which are in the nano level. A flu virus, which is 100 nanometers. A bacterial phase, 60 to 70 nanometers. And the gold particles, 30 nanometers to 50 nanometers. And nano clay is also related to that. Gold particles and nano clay. And DNA, which is 2 nanometers. That is the least size which we have. The small comparison for that is 12756 10 to the power of 12 times to the arch diameter. That is a small comparison which have nano means that much size, that much less in size. So this is a small comparison. So now we'll see particularly in the nanotechnology how the nanomaterials are divided. So the nanomaterials, particularly we have a 0-dimensional materials, 1-dimensional materials, and 2-dimensional materials. So 0-dimensional materials means in that particular 0-dimensional materials, all the 3 dimensions are in nanoscale. You can see it here, the first one, nanoparticles. So all the 3 sizes like thickness, length, width. So all the 3 dimensions are in a nano level. When the 3 dimensions are in nano level, then we call that as a 0-dimensional material. Next one is a 1-dimensional material. 1-dimensional material means 1 will be in the nano size. Sorry, 2 will be in the nano size and 1 will be not in the nano size. You can see the diameter is a nano level, width is also a nano level, but the length is not in the nano level. Nanofibers. So the nanofibers. So all these materials we can see like a bulk materials only. We can't see as a single material with our eyes. So other third one is 2-dimensional, that is a nanoplates. So in this only 1-dimensional will be in the nano level. The other 2 is not in the nano level. So the thickness only in the nano level, the width and the length are not in the nano level. So these are the 3 terms which are in particular in nanotechnology. And 3-dimensional materials like that are visible, all the 3 dimensions are not in a nano level. So we'll have a 0-dimensional, 1-dimensional, 2-dimensional, 3 different type of materials. So this is about nanomaterials, particularly in a nano composites. We'll have a polymer based nanocomposites. We can prepare a polymer based nanocomposites. Non-polymer based nanocomposites also we can prepare. If it is a non-polymer based nanocomposites, one is metals, ceramics, ceramic nanocomposites. So these are the different type of materials like polymers. We can use polymers, inorganic, hybrid, and polymers, layered silicates. So by using the polymers, we can prepare. By using the non-polymer based also, we can prepare nanocomposites. So the basic term, like when we are preparing nanocomposites, so maybe earlier already speakers talk about the preparation of nanocomposites. So I'll start with the preparation of nanomaterials. So how we prepare nanomaterials, and after that, how we incorporate those into composites. So the first thing is we need to learn how to prepare a nanomaterial. Basically, when you start a research or any type of a work, basically what we do is like, instead of going, if your objective is to prepare a nanomaterials, then you'll start developing the nanomaterials. If your objective is not to prepare a nanomaterial, if your objective is to prepare a nanocomposites, then you don't prepare nanomaterials. Straight away, we will purchase those nanomaterials which are available in the market, and we'll start working with those nanomaterials and then fabricate a nanocomposites. So instead of purchasing it, if you prepare your own nanomaterials for your research, then that will be more advantageous, because to purchase a nanomaterial, the cost of the nanomaterials will be higher. If you develop your nanomaterials, so when you are developing the nanomaterials, you can vary the designs and you can develop different type of nanomaterials, different shape of nanomaterials. So we'll see some fabrication techniques which are related to nanomaterials. So in the preparation of nanomaterials, we have two methods. One is bottom up method. Another one is top down approach. One is bottom up approach. Another one is top down approach. So you can see it, top down approach is like we have a bigger material. In the top down approach, we have a bigger material. So we'll cut that material into smaller pieces, and then again we'll cut into a smaller pieces and make it a particles. So this is a top down approach. Another one is a bottom approach. In the bottom approach, we convert that into liquid state. The solids will be converted into liquid state. And after converting into the liquid state, again, we are developing that structure from that liquid state to solid state. So converting from the liquid state to solid state at the time of a development, so we develop nanoparticles. So that is bottom up approach. So we'll see some examples of fabrications of materials. So this is a top down approach, like a mechanical grinding. Later, we'll see in depth, like how this mechanical grinding will go and everything. So mechanical grinding means two balls will come and contact. When the material come between these two balls, automatically that will be break into a small pieces. So that is about the mechanical grinding, that is top down. The bottom up approach, in this picture you can see it, the solid phase convert into a gel, a liquid phase. So after converting into the liquid phase, again we'll develop the structures. So we'll see one or two examples. The preparation of alumina. So first, before going to the preparation of alumina, let me introduce what is alumina. Alumina is a ceramic material. It's not a metal. It is a ceramic material. This alumina will be available in gamma phase and alpha phase. In two phases will be this alumina will be available. So this is a ceramic material which having a melting point of 1600, and this alumina can be used as a lubricant or a coolant. Nanoparticles will be used in all these applications we have, and these having a high tribological properties, and it also increases the strength to the materials. So these nanomaterials, when you purchase from outside, the cost of the nano particularly will be very high. Instead of purchasing it, we can easily fabricate these nanomaterials when we have aluminum nitrate or a glycine or citric acid, any one material, and some glass beakers and one magnetic hot plate and one furnace. So these are the equipment required to fabricate a nano alumina. So the chemicals which were required is aluminum nitrate. We can go for a glycine or citric acid as a combination. So these are available. The cost of these materials also, like 1 kg of aluminum nitrate costs you almost 600 or 700, and citric acid also approximately to 500. So those two chemicals are available in a solid state. So those two materials with the mole fractions, taking a 1 mole fraction of aluminum nitrate and 1 mole fraction of citric acid or a glycine, anyone, we can mix it with water. So all these two chemicals, these two are available in a solid state. Easily we can mix using water. We can mix with the water. After mixing the solution, we can keep it on a magnetic hot plate. So magnetic hot plate means like, or maybe you have seen it, and the a magnet will be placed inside, so that a stirrer will be placed inside the beaker. When you switch on that, automatically the magnet will rotate, the inside stirrer also start rotating and self-rotating. So this solution we need to kept on a magnetic hot plate and start the machine and then keep it for 50 degrees. So after 2-3 hours, the entire water molecules, because we added a water, and you can see the equation, the aluminum nitrate, it having a 9H2O. This also having a more amount of water. So these water molecules, along with the added water molecules, start evaporating slowly. So the entire water will be evaporated. Once the entire water will be evaporated, then the remaining material will be formed as a ash kind of content. Ash material will be formed in that beaker. So that ash material, we need to take that and then put in the furnace for 8 hours. And the temperatures we can vary from 800 to 1000. As I said, like alumina is available in two forms. One is a gamma alumina, another one is alpha alumina. So if you burn at 800 or 600 or 700, then surely the alumina which is formed will be a gamma alumina. From 800 to 1000, you will get alpha alumina, which is a pure forms of alumina, which is a pure ceramic. So we need to check, we can vary the parameters like 800 to 1000, we can vary, and then in the least temperature, what best material we can, what best alumina we can get, that we need to check when you are developing that alumina. So 800 to 1000, we can vary it in the furnace. After that, we'll get a pure alpha or gamma alumina. So once you get that particles, then you need to go confirm whether you got alpha alumina or gamma alumina, or whether that material which you fabricated are in the nano level or not. That also you need to check. So for that, you required some characterizations. So some characteristics like SEM analysis, TEM analysis, and XRD analysis. So FTR analysis, all these are required to prove whether the formed material is an alpha alumina or a gamma alumina, or whether that material is in a nano range or not. So this is a work which I carried in my PhD. So I developed this alumina. So some results straight away, like without in the slides, I tell you, like when you use aluminum nitrate and citric acid as a combination with a 1 mole fraction, both, you will get the least nano size, which is almost 70 nanoparticles. But this is a bottom-up approach because we are developing from the low level, like converting the solid state into liquid state, and then we are developing it. So the maximum amount of particles which is formed will be in the range of from 70 to 100. Within that range only will the formation will be there. But the temperature which you are at 900 degrees centigrade only, you will get the pure alpha alumina. In 800, it is a partial. It's a combination of alpha and gamma. So another technique, this is a top-down approach. It is ball milling. So this is a mechanical process. Earlier one is a chemical process. So in the preparation, we'll have two processes. One is a chemical process, another one is pure mechanical process. So in the mechanical process, so directly, simple terms, we can understand means like, if you want to convert into a particles, the best way in our houses, which we have is a mixie. We'll put all the things in the mixie and then we'll run it for 5 minutes. Then the entire solid structures will be converted into small pieces. The same process will be adopted in this ball milling process. So in the mixie, we'll have a blades. Here in the ball milling, we have a balls. A small different sizes of balls will be there. That balls will place inside the planetary ball mill in the beakers. And then whatever the material which we need to convert into a nano size, that also will place inside. And we'll run planetarily like for hours, like 5 hours, 10 hours, 15 hours. It depends upon the material hardness. So after running for the hours, due to continuous rupture between the balls and this material, the material convert into a small size. The bigger material, micron material, are convert into nanomaterials. So that's what happens in the ball milling process. So sometimes this process will be done without any coolants, without any liquids. So wet milling, without dry milling, we can do it. Sometimes these materials sticks to the containers, beakers. So in that condition, we go for a wet milling. So when we go for a wet milling, then we need to go for a filtration process. So we need to filter it, and after filtration, directly we can separate that nanoparticles. And the problem with this particular mechanical process is we don't get the uniform size. The range of the particles will be a bigger. As I said, in the chemical process, the range will be 70 to 100. But in this particular ball milling process, the range will be a bigger. Like we can't get 70. If the balls are very low, we can get from 70, it may be 200. The range will be bigger. Because these materials, it's not a continuous form, it's a random breaking of materials. So we don't get the uniform size of the materials. That is a disadvantages with this particular mechanical process. So there are two processes to prepare it. So in this example, you can see it, the fly ash materials are converted into nano shape. So we kept the fly ash particles in the beaker, and then we run for hours, 8 or 9 hours. Later, we use Tolan as a material to have a wet milling. So after that, we filter the materials and the Tolan will be dried, automatically vapored. And finally, we'll have a nanoparticles. The fly ash will be in a nano level. So these are the two processes which you can develop your own nanomaterials based upon the applications, based upon the materials which you selected. Next, why we need to go for these nanomaterials? So what are the advantages? So particularly why nanotechnology? Why nanotechnology is popular? Nowadays, we are going towards nanotechnology and we are trying with nanomaterials, nanocomposites, because already we have composites, we have continuous fiber composites, we have micro composites. Now we are trying with nanocomposites. What is the advantages with these nanomaterials? So that we'll see few advantages with these nanomaterials. So already I explained this slide earlier, like definition of the nanocomposites, because we slightly moved to preparation of nanomaterials. Again, to come back to the nanomaterials, I have given this definition again. So one dimensional will be in the nano level. So we'll see what are the advantages in it. So let us take, in this picture, a small cube is taken. The surface of that cube will be calculated. The side of the cube is 5 centimeters. So height is also 5. Then the area of that cube is, the side of the cube is 5 into 5, that is 25. And it having a 6 faces, then 5 into 5 into 6, that is 150. The surface area of that particular cube is 150. So when I cut the material into small pieces, like I'd cut the material vertically and horizontally 5 to make it a 1 mm cube. When I convert this cut vertically and horizontally as a 5, then I got almost 125 cubes. Now the side of the cube, small cube, is 1. So 1 into 1, and the 6 faces 6. So 125 cubes I have, 125 into 6, that is 750. So now you can see that the surface area is 750, which is 5 times to the earlier surface area. When I assembled all these 125 cubes, then I'll get a surface area of 150. When I separate all this, the surface area is increased. In a simple other terms, easily to understand it, let us take one book. If I place the book on the top of a floor, which is a 200 pages book, when all the papers are in a tight, in a single bond, like when we place that in another floor, the book only covers the page size. So the page size only, it is covered by the floor. When I cut all the pages, when I separate all the 200 pages, when I start spreading the entire floor, that book covers the entire floor. So what I did is, earlier that book is 200 pages book, I kept at one place. The area covered by that only the page size. But when I cut all the 200 pages separated and then spread on the floor, then the entire floor is covered by that book. So you can imagine that when you cut a bigger material into smaller material, the surface area is increasing. So someone please mute your mic.
Sir, shall I mute everyone, sir, so that they can unmute?
Yeah, later like
Raise, yeah. Sir, I muted you also. You have to unmute, sir. Mute all I have. Hello? Sir, please unmute yourself.
Yeah. Hello.
Okay.
Yeah. So in this example, as I said, like if you spread the papers entire floor, automatically the entire floor will be covered with that book. The single book, when it is at one place, the page size, covered surface area. When I cut the 200 pages and then spread, the entire floor will be covered. So that is an advantage with the nanomaterials. The second advantage, we can see it here. So in the picture, if you see it, this is the, to understand it clearly, we have given a picture here. In a polymer plate, we inserted 1 micron particle. So in the picture, like a polymer plate, 1 micron particle is inserted. So that micron particle covers the contact area between the polymer and the micron particle. The black line tells you the interface area. So in a composites, if the interface area is good, then the strength will be increased, because the interface area is a very important. Basically, these composites are the materials, like when you are developing any type of a materials, composites, we are disturbing the structure of the polymer. Like for example, if you are developing a polymer composites, the structure, the atomic structure of the polymers are disturbed by these. So when you are disturbing it, there won't be a chemical bonding between that material. There will be a physical bonding. When a physical bonding occurs between that material, between the matrix material and the micron material, particle material, the interface is very important. When the proper interface takes place, the interface strength is higher, then the load transformation will be in a better way. So the interface is important in the composites. So here the interface area covered by this particle in the polymer is approximately, it is calculated as 4%. The particle covered is 6%. So in this plate, the black circle covers only 4% in the entire area of the plate. This particle covers 6%. So after that, by using a ball milling process, if we cut this material into smaller pieces, so by putting in a ball mill and then cut into a small pieces, as I said, micron particle, let us take 1 micron, the size of that is 1 micron particle. If it is a 1 micron particle, then I can make that material into, if I make a 2 nanomaterials, size of a particle will be 2 nanometers, then I can cut that material at most 500 times, like 500 particles I'll get. So if I cut this micron particle, 500 times we can cut it to make a 2 nanometers particle. So when I cut 2 nanoparticles, 2 nanometer particles, and then if I spread into entire plate, you can see here, the entire particles again covers a black zone. So the entire individual particles have an interface. So the particles covered by it is 6% only. The area covered by that particles is 6%, because the particles when you assemble are separated, there won't be change. So the particles covered is only 6%, but the interface area is increased to 45%. So from 4% it is increased to 45%. So means the particles coverage in the particular plate is increased and the interface is increased. That is another advantage. So we'll see one simple term here. About a little bit like crack propagation. So let us see, like if I have a crack is initiated here in the polymer. So if a crack is initiated in that polymer, automatically that crack has a capacity to break the polymer. Once the crack has a capacity to break the polymer, then automatically it flows entire polymer. So for example, let us take a crack is initiated here. It will pass entirely through the polymer. So it won't stop, because the crack has a capacity to break the entire polymer. But in this case, when the crack has a capacity to break the polymer, when it comes to this point, at this point, automatically interface will stop that crack. The crack won't allow the interface area, interface bond won't allow the crack to propagate through it. Automatically the crack can take a deviation along with this and travels out. Or if the particle is weaker, it will pass through it. But when it comes to the interface area, it will stop for a certain time, and there will be a possibility to take a deviation and pass through the interface and again break the polymer, or it passes through the material after breaking that material. So, but in this, due to this material, due to this particle, the interface, due to the interface area, due to this particle, the life of that particular composite will be increased. If we have this particle, if we don't have a particle directly, once the crack has a capacity to break the polymer, it continuously break and then fracture the total polymer. But here the crack will stop and then take a deviation for a longer time. So the life of that material will be increased. If you see in these particular composites, in the other composites, if a crack is initiated here, it will come and stop here. As earlier, it may take a deviation or it may pass through it. Again, when it comes to this particle, again, it will stop for a certain time. And again, it will take a deviation. Again, it will come to here, stop and deviation or pass through it. Again, it will come here, stop here, take a deviation, stop here. So before reaching it to this point, almost 5 times the crack is stopped and then take a deviation. So you can imagine the lifetime of that particular material will be increased when you're having a nanomaterials. So when you have a single material, the propagation will be less. That's why, like if you see it, the constructions, particularly in a construction point of view. So in the olden days constructions, they use different type of materials in their construction level. So they didn't use only 1 or 2 materials. They use different materials when they're constructing it. So that's why like the life of that particular structures are very high, because the crack propagation, the main defects are about the crack propagation. Once a crack is fully propagated through the thickness, automatically the wall will fall down. So what material will stops that is the new materials continuously. When there is a interacting with the new materials, new interfaces, then the life of that particular material will be increased. So that's why, like, even if you see the walls, the construction of our houses, they used cement bricks, cement, sand, different materials they used it. So that's why, like, when you see the cracks are propagating on the top of the wall only, not along with the thickness of that, because in the thickness, they have a different harder materials when compared to the cement. And these are discontinuous materials. So inside we have a continuous brick materials, which are having a more harder when compared to the outer surface. So that's why the cracks are propagating along with the surface, not through the thickness of that wall. So that is another advantages with particularly with nanomaterials. So these are the some advantages with the nanomaterials. So next one is there is how to prepare a biocarbon. Like as I said, these are conventional nanomaterials. Like for example, alumina preparation, again from the chemicals we are preparing it. And for example, fly ash, again that is will be industrial waste. That is one advantage, like from the industrial waste we are using it. Another thing is like how to prepare a nano biocarbon. So what is the main importance of this is, particularly when you are preparing a biocarbon, so how you prepare a biocarbon, what are the uses and why we go for a biocarbon, first we'll discuss. Like developing of a biocarbon is important because when you are preparing a biocarbon, the applications of the biocarbon will be increased. So when you are preparing those materials, so that can be replaced with the conventional carbon materials. And in the nature, as I said, there are different materials which are available. And those materials we can use, we can show different applications. Like for example, if I take an example like water filters, in our water filters, if you see the different type of filters, the first filter we have is the carbon filter. So that carbon filter, that carbon particles that prepared by using coconut shells. So if you search in the online, you can see it, the coconut shell materials are used to prepare that charcoal. So it's not from the coal, it's a charcoal, like those are prepared from the coconut shell chips. So those coconut shell chips, they use it to prepare the carbon materials. So particularly when you are using these natural materials, if you don't use these natural materials, coconut shells, they directly decompose in the atmosphere and again they release the carbon. Basically the entire lifetime, the natural plants absorb carbon. After that, again they decomposes, again they release the carbon. So if I use this carbon for different applications, then automatically the pollution will be reduced and the usage of these waste materials also increased. And the cost of the final components also reduces. So that's why, like in the example, you can see it, the coconut shells crushed and then chips, you put in the ball mill, and after that we'll have a raw powder. That raw powder we can put in the furnace in an inert atmosphere, and then we can have a carbon char. So it consists of a fixed carbon and allied carbon. Again, I'm not going deep into it, the pyrolysis process and all those stuff. The carbon particles, when you put in my inert atmosphere, then automatically you will have a carbon particles, the charcoal particles. It depends upon the size, whether you are going for a micron particles or big sized chips or a nanocarbon. Depend upon the sizes, again we'll have a carbon char. So that carbon char, again there are two different methods like activation methods. So one is single step and two step. A single step means directly milling it, converting it, and then directly by physical or chemical activation, burn at different temperatures, 400 to 1000, and then wash it. Another one, two step, is preparation of a carbon in the single step and activate that material, and then again burn the material. So why we go for activation later, like if it is, that will be like a different concept, because some materials will be break at, some bonds will be break at lower temperatures, some bonds won't break at low temperatures. Like for example, the carbon which is formed with the different bonds, those bonds break at 400 degrees centigrade. Some bonds will break at 400 degrees centigrade. Some bonds won't break at 400 degrees centigrade. So we need a high temperature. Instead of going to the high temperatures, we go for activation of the materials. That is a different concept in the pyrolysis. So this is the steps like involved in the fabrication, as I already said, like raw material cleaning, drying and grinding, and activating the materials, and again drying it and carburizing at 800 degrees centigrade and washing with the different materials to remove that activated materials. So this is activation carbon process. So we'll have a carbon in the picture also, you can see it. These are the carbon particles when you are burning at a different temperatures. So we'll have a nanomaterials, like these bigger size materials. When you are burn at different temperatures, that particles will burn and then converting into different type of carbons, combination of nanomaterials and bigger particles. And again, finally, if you burn to a higher temperatures, these nanomaterials will be absorbed. This is a nanocarbon. So once you prepare any type of a nanomaterial, you need to prove that the fabricated material is in the nano level. So for that, we'll go for a SEM analysis or TEM analysis or XRD, some other techniques we'll use it to prove that the fabricated materials are in the nanozone. So some applications, many speakers already talk about it, like energy applications we have, medicine, drugs, nanotribology, nano devices, and different nano fabrics, cosmetics, all these are the applications of the nanomaterials. So some statistics like in different areas like chemical manufacturing, how much amount percentage will be the aerospace and other applications, electronics and pharmaceuticals, all these, like what are the different percentages of this nanotechnology involvement. So coming to the fabrication of a nanocomposites, maybe a few of the speakers may talk about this fabrication. Basically polymers, if I talk about the polymers, then the basic technique which we have a composites is a hand layup technique. So we can prepare the composites by using a hand layup technique. So in the hand layup technique, we required a mold. We can prepare a mold on our own, and we need to select some polymers which are suitable for the applications. And if you are going for a nanomaterials, like as we are discussing about the nanomaterials, we'll talk about only nano things. So if you select a nano fillers, we can select one or two fillers, and we go for a certain calculations related to that molds, and then some equations related to it, and we design those things and we'll mix it and we'll pour into the mold. So this hand layup technique is a traditional old technique. This is a first technique, as people know about the castings. So the casting technique is the first basic technique. After casting, we'll have, due to different disadvantages, different problems in the castings. So further classification of the casting came into existence, like low pressure casting, high pressure casting, centrifugal casting, die casting. So many casting techniques came into existence, investment casting. So those casting techniques came into existence after identifying defects in the castings. So this is a traditional technique, hand layup technique. This is the first basic technique which we have for the composites. So in this composite technique also, there are different disadvantages. So to remove that and to reduce that disadvantages, people modified this technique into spray up technique, filament winding, pultrusion technique. There are different techniques for fabricating of composites. So by using a hand layup technique, we can easily fabricate composites, because in a normal labs, we don't have a filament winding process or a pultrusion technique or a vacuum bagging technique. So this hand layup technique can be used in a normal colleges or normal in your house also. You can develop small components, because in the YouTube nowadays you can see it. People are developing the furnitures or different aesthetical components by using a normal layup. So you also develop when you know the certain calculations, how to mix the polymers and how to combine these things with the different materials. So this is a technique. A roller is required and a mold can be prepared. Once we mix the calculations, how much amount of volume fraction we need to go for the reinforcement and matrix. After that, directly we'll mix it and then we'll pour on that. For a rolling process is applied to make it a uniform structure. And once a uniform structure is formed, then we go for curing it. Once it is cured, then we'll go for a finishing process of those composites, and finally we'll have a composites. So this is a hand lab technique. This is sintering casting, stir casting. This is like metal matrix composites. So earlier will be particularly hand lab technique will be particularly belongs to polymer composites. So in the hand lab technique, we can't fabricate a metal matrix composites. So this concept, a nano particulate metal matrix composites. To prepare a nano metal matrix composites, we go for a stir casting. The stir casting is a basic technique. Again, in that also there are modifications. The stir casting with mechanical stirring process and ultrasonication. Ultrasonication also we can do it. So the mixing of the materials are important in the stir casting process. So when we stir the process, when they stir the metals, then we need to see that nanomaterials won't settle down at the one portion or won't form any agglomerations. Basically, the problems which they face when they are preparing the composites are all the particles will be settled at one portion, or all the particles will be forming an agglomerations in the material. So due to that, again, whatever the composite fabricated, it has certain defects. So to avoid that, we need to see certain modifications to the process so that we can avoid the settling of that nanoparticles or formation of the agglomeration of that nanoparticles. And we need to see that the entire particles must be uniformly distributed in the entire structure. Whatever the material which finally we are fabricating, we need to see that the entire particles may be uniformly distributed in the entire composite. Then only the composite will be formed in a proper way so that the strength will be increased. So that is about the stir casting process. It having a mechanical stirrer, which is connected, and mechanical stirring plates will be connected here, and the particles which we have will be poured here. All the particles will be pouring in the chamber, and this is a molten material. And when you are continuously stirring it with those particles, after that the bottom pouring will be done directly. This will be opened, and then bottom poured will be done here. So to make it in an inert atmosphere, we'll create an argon gas so that there won't be any oxidation effects, because metals, when you are heating at a room temperature, in a high temperature melting level, then automatically if you are conducting in a normal atmosphere, the oxidation effect will be there. It reacts with the oxygens and form oxides. If you are using an alumina or some other materials, so then it forms aluminum oxide or some other materials will form. So due to that, to reduce that oxide formation, we go for argon gases. So that is a concept which are related to stir casting. So before this, a few minutes can ask some, like if anybody having any questions, so that for a few minutes, we'll take some questions and then we'll continue and we'll have certain calculations. Now, if anybody having any type of a questions are related to up to the covered topic. You can write in the chat box. I think all the mics are muted, so it's not possible to unmute your mics. So you can write in the chat box so that I can go through that and then I can answer that.
Participants can raise the hands. If you are raising, then I can unmute your speakers. Sir, how to ensure uniform dispersions of nanoparticles in alloy matrix during stir casting?
Yeah, how to ensure actually the main problem is when you are designing or when you are selecting a material, uh, first we need to see that what is the densities of those materials. For example, let us take alumina. Alumina density is approximately 2.4, 2.5. If I select a nanomaterials which having a density of 8 or 9, then when I add that, then automatically when I add into that stirring process, all the particles will settle at the bottom. When I pour in the bottom pouring, all the particles will fall down first, so that all the particles will be in the corner portion and the remaining in the top, I have a metal. So there won't be a uniform distribution inside it. So that's why like when you are selecting a material or when you are designing the composite, you need to see the densities of that. If the densities are higher, then we need to see other alternate technique, not for exactly going for the stir casting process. Even now people are facing problem with that stir casting. So what they are doing for is ultrasonication, like ultrasonic stirring. But still in the ultrasonic stirring also, the particles which having a high denser, there is no solution for that. So that's why people nowadays what they are selecting is when they're going for a particular metals, they try to see that the both the densities, the particle density and the metal density more or less equal, so that the particles may be easily distributed. Still, there is a problem in that when they are adding these nanomaterials or micron materials, like when they add it, those materials form agglomerations. So that's simple solution is that instead of straight away pouring the particles at one point, if you see in the slide, all the particles are pouring at one point. Instead of pouring all the particles at one point, at different points, if you pour the particles, then automatically all the particles won't be settled at one portion, and all the portions, all the particles are placing at different points. So easily there may be a chance of mixing the all the particles. That is a one advantage when you are not pouring all the particles at one point. When you are placing in a different places, then there will be a more chance of mixing the particles. And 99% we can't say that all the particles are uniformly distributed. So to prove that, what people do is like where there is a uniform distribution, there they will take the SEM analysis and then they'll show it in my composite, the strengths are like the particles are uniformly distributed. So, but truly speaking, like there won't be such chances of uniformity mixing of all the particles, particularly in a stir casting process. One more question, like if people are related to composites, or if they want to know the calculations related to hand lab technique, then I'll discuss that. Otherwise, I'll continue with the characterizations. So calculations related to the fabrication of a composite. Because to fabricate a composite, we require certain calculations. So without knowing the calculations, we can't easily fabricate it. If people are interested to know the calculations, I'm not getting the chat box. Earlier I've seen it. Yeah, I got it. Yeah, one question is like, can you provide some inputs on how to avoid voids in nano composite fabrication? Okay, yeah. So first, let us take polymers. To avoid the voids in the polymers, one option which we have is after fabricating, after mixing the materials, to avoid these voids, we can go for a vacuum bagging. So keep it in a vacuum container and to remove the entire air so that the air bubbles will be removed. Or when you are going for a stirring process, go for a better stirring process, not for a mechanical stirring process. Go for a ultrasonication so that the particles may be mixed uniformly and less voids will be created. And another thing is like when you are pouring it, like when we are preparing a plate kind of a structure. So when we are pouring it, don't pour all the particles at one place. Try to spread the pouring in the entire plate, not pouring at a one place only. But what the people do is they will pour all the matrix at one end and then they are allowed to flow to the other end. So instead of that, you pour the materials in the entire plate so that the voids will be stretched and then the voids will be removed. The air bubbles will be removed. So these are some techniques like when you are developing a polymer composites. So when it comes to the metals, in the metallic case, the void content formation will be less, oxidation formation will be higher. But in the polymers, we'll have a more amount of voids will be formed. So to reduce that, these are the some techniques which we can do it. If you don't have a vacuum bagging technique, then you can, instead of pouring at one portion, pour in the entire plate, like whatever the mold which you have created, pour in the entire mold so that the voids will be reduced and air bubbles will be removed. That is one solution. So regarding that particular calculations, nobody say require the calculations. Then I'll directly go to the density and void content. So the next 20-30 minutes, I'll continue the lecture and then later we'll discuss any questions. So in the composite fabrication, or a nano composites or a normal composites, we need to calculate the density. Density is a very important. And the next one is a void content. So calculation of a density. First, in the coming to the density, we'll have two terms in the density. One is a bulk density and a true density. So true density is a real density. Bulk density, when you are calculating for a particular material of a powder, if you want to calculate the density, we'll get a bulk density. So for the powder, if you know using a formula mass by volume, then that is a bulk density material. It's not a pure density. So to know the pure density, we need to use an Archimedes principle. So using a pygnometer. So in the pygnometer, directly take the material which we need to test the density. And these are some formulas like W naught by W naught plus WA minus WB. The terms also bottom you have written, like weight of the sample, bottle plus kerosene, weight of the sample plus bottle plus kerosene plus sample. So by using this formula, we'll get the specific weight of the particular material. And to know the density, we need to multiply with the kerosene. Like if you are using the liquid as a kerosene, then we'll go for the density of a kerosene. If you are using the water, we can go with the water. Like whatever the material, like liquid, which we are using in that pygnometer. So this is a to know the density of a material, we need to dip that material into that beaker so that how much amount of liquid is expelled in that. And coming to the void content calculations. So this void content can be calculated by theoretical density minus actual density by theoretical density. So void content can be calculated by theoretical density minus actual density. Actual density we'll calculate by using this formula. So theoretical density we'll calculate by using this formula. Right side we'll have that formula, 1 by weight fraction by density of that fiber plus weight of matrix plus density of matrix plus weight of particles by density of particles. So if you are not using a fibers, directly particles will be there, particle densities will come. If you are using the fibers and particles, both will come. So this is about the actual density and theoretical density and actual density. So by using that, directly we can calculate the void content. So once we know the void content of that material, then directly we can, when you are showing the any type of results, then directly we can show how the results are affecting due to these void contents. So sometimes there is an increase in strength and sometimes there is a decrease in strength. So when there is a decrease in strength, we can justify that decrease in strength by giving the values of the void contents. So due to these void content, the strength of the materials is decreased. Basically here one point to be remember, the theoretical densities, the theoretical values are very high. The experimental values are very low. Because when you calculate theoretically, you are considering ideal conditions, and when you are considering that ideal conditions, the values are very high. When you are considering the real values, like experimental values, the values will be very low because there will be material defects, manufacturing defects, testing defects. So all these defects finally leads to less runs. So there will be a huge gap between theoretical and experimental. So that's why, like, when you are comparing that, then automatically we need to show these wide contents, which reduces the strengths. So coming to some analysis of the nanocomposites. So this is a tensile test. Using a dog bone shape, we'll conduct a tensile test. Once the samples are prepared, continuous fiber composites or particulate composites or nanocomposites, then we'll go for a testing of this using a tensile test method, UTM. So a dog bone shape is prepared, and this is the shape of that material. If it is a continuous material, then we don't go for a dog bone shape. So for a particles, nanocomposites, then we can go for this dog bone shape material, and then we can test it. So already you know that the maximum load is applying where we have a less cross section. So that's why the load will be applied on this zone, the gauge length. So that's why the shape of this one is a tapered here. This is a bigger diameter, this having a less. The entire load is applying on this zone. And in that particularly where there is a surface defects or internal defects, there the entire load will be affecting on that. If none of them having a defects, then the failure will be in the center. So next one is compression test. The compression test will be applied in the same UTM. It will be in the opposite direction, load will be applied. And the fibers, if you are fibers, buckling will take place. If you are particles, the breakage will take place based upon the material, like whether it is a ductile material or a brittle material. If it is a ductile material, then elongations will be there, then the length will be converted into width. If it is a brittle material, a sudden fracture will take place and breakage of material will observe. That is happen in the compression. So here you can see it in the picture directly. When you are compressing it, the length is increasing and length is decreasing, the width is increasing here. Another test is a bending test. So whatever the samples, whether it may be a nanocomposites or a normal, then we go for a 3-point bending test. So two supports in the center, we are applying the load. So when you are applying, the bending will take place. When the length supports are bigger, higher, then the shearing will be less. Shearing will be there. We will assume that as a negligible, and maximum bending will be taking place. So there will be a bending load here. The shearing of the load will be less. So the same thing, interlaminar shear stress, the same type of 3-point bending test, but the length is very less. Length will be half when compared to the earlier one. So in that condition, shearing of the layers will take place and bending of the fibers will be very negligible. So when the bending is negligible, we'll have a shearing loss. That's why the interlaminar shear test will be done. So the shearing of the fibers, we can see it here, are the particles. So these are some characterizations which are related to nanocomposites or general composites. So once when you are developing any type of a composites, once you are testing all the mechanical properties, sometimes we'll have a disadvantage. Like sometimes we don't have the exact result, required results. Then automatically we go for change of materials. Basically, instead of going for a change of materials, if you test the other properties, like instead of mechanical properties, if you go for tribological properties, then the tribological properties may enhance. So when we have a better tribological properties, instead of showing that applications related to mechanical, you can show that composites are materials in terms of tribological point of view. So this is a one pin on disk. This is for abrasion test. So in the picture, you can see it. So that will be a pin will be whatever the composite, nanocomposite, which we can develop. That will be in terms of a pins that will be placed here, and the top of the disk that will be rotated. So that composite pin, nanocomposite pin, how the wear resistance will take place due to addition of these nanoparticles, that will test and compare. So some values related to it, this will be conducted by weight loss method. So initial weight of the composite and final weight of the composite will take, and then we will calculate that using a weight loss method, and a wear rate will be calculated. So these terms, calculations, when you are conducting a wear test, abrasive wear test. So when the two materials are in contact, due to wear, how the material loss will be there, that will calculate. If mechanical properties are less, then we'll check for the tribological properties. The another test will be erosion test. So this is a sand impact test. This is another characterization. So when the sand impacts on the top of a material, here in the picture you can see it, when a sand impacts on the top of a material on the composite, so how the, due to impact, how the material loss will be on the top of the surface with the different angles. We can vary these angles in this apparatus. So we can vary from 30 to 90 degrees, and we can see how the material behaves with a different angle of impacts. So when we fabricate a nano composites, then we can see due to impact how the material behaves to the different velocities as well as different angles. So this test also used calculated by weight loss method. So initial weight and final weight of the materials will be calculated, and that will be tested. And the formula is delta W by WE. That is the total mass of the rodent of the particles and the weight loss. So some characteristics, like when you prepare any type of a composites, it depends, like when you are using a different materials, percentages also changes and materials also changes. You can see in the picture, like the carbon fibers and the glass fibers. This is a one taken from one journal. So 60% of the glass fibers, the strength is low. In the very starting, I said glass fiber strengths are low, carbon fiber strengths are high. So 30% of the glass fibers giving more strength. If you see the strengths here, it is almost 150, it is almost more than 200. So 30% giving more when compared to 60% glass fibers. When it comes to the densities, density point of also, here the density of the glass fibers are higher, the carbon fibers are lower. But cost point of view, the glass fiber, carbon fibers cost is high. Again, if you see when you are changing the polymers, the performance, the strengths of the polymers, like due to the polymers also it varying. Like you can see it, the first material having almost 150. When you change the polymer, the strength is increased. And when you change the one more polymer, the same compositions, the strength is decreased. So the densities are slightly varying, but if you see the values, due to change in the polymers also, the properties are varying. And due to the percentages changing also, properties are varying. And the material changes also gives you change in properties. And particularly this is about the orientations. Like when you are changing the orientation of the fibers, when you are applying the load in the same direction of the fibers, then you will have a high strength. When you are changing the directions in different angles, 22 degrees, 45 degrees, 65, 67 degrees, and 90 degrees. So when the load is in particular opposite direction, then you can see in the picture, the strengths are decreased. It having a high strength when the fibers are in the same direction. Strength is decreased, 45, and 67 is still decreased to a higher end. And it is decreased more than the polymer strength after addition of the continuous fibers. So the application of the load and the fiber directions are very important. Even the particles are particularly the continuous fibers. The orientation of the fibers are important. In which direction we are applying the load. If in that direction, if you have the fibers, then the strength of the composites are more. If you don't have a fibers in that direction, then the strength is less when compared to the pure polymers. And the combination, like composition, when you are increasing the compositions, how the strengths are increasing. So when you are increasing the nanomaterials, the strengths may be increased sometimes, and then sometimes it may decreases. Like you will see it, 10% it is increased, 20% it is increased when compared to the pure polymers. Then after 20%, when it is going to 30%, it is decreased. So this may be happen due to the agglomerations, and there won't be a proper wetting ability of that particular polymer when it after reaches 20 degrees centigrade, 20%. So more than 20%, the wetting ability of that particular polymer will be reduced, and then the solid content become more dry content, and there won't be a proper bonding between that, and still some agglomerations will be formed. Due to that, the strengths will be decreased. So this is what happens when you are going for a higher fiber loading. So some results to show the nanocomposite values, like these are my PhD results, like epoxy, a pure polymer, inserted a glass fiber composites, the strength is increased. So jute fiber comparison, the strength is not up to the mark, like natural fiber replacement. So this is almost only half of that material strength. So we can't straight away replace these jute materials, natural materials with this conventional materials. So that is compared with flexural strength and flexural modulus, tensile modulus. All the results are same. So instead of going for a plain composites, next concept is going for a hybrid composites. So addition of a hybrid composite. So instead of plain jute material, combination of glass and jute, still none of the materials have a capacity to replace the continuous 4-layer composites, glass fiber composites. So in all the results, the glass fiber composites are showing better results. So the next technique, what we go on is a micro particles along with this hybrid composites. So along with the hybrid composites, we added some nano fillers and micro fillers. So to increase the strengths, whether there is a chance of increasing of the strengths or not, still none of the materials are capable to replace straight away with these conventional glass fibers. So we gone for a nanotechnology again. So in the nanotechnology, what we observed in this flexible strength, you can see it, some materials with 4% nano fillers and with glass as a outer layers and glass as a middle layer, giving the better results when compared to the pure 4 glass composites. So the glass as a outer layers or glass as a alternate layers with the 4% nano fillers gives the best results when compared to a pure glass fiber composites. Then instead of a pure glass fiber composites, so 2 jute fibers plus 4% nano fillers can replace that materials. So these 4% nano fillers are material which is generally available, like these are the nano materials which is fabricated, and these jute materials are natural materials. So these conventional glass materials can be replaced by these materials. So these are some results. To get a better comparison, this is a one picture. Here you can see it, 0% microfillers, means pure glass as outer layers and jute as inner layers, and 5% micron fillers, strength is increased. When you see, compare within a 5% micro technology and 2% is nanotechnology, so nano composites, the strength of the nano composites are higher when compared to micro materials. So that is an advantage with these materials. So nanotechnology, even when compared to the micro materials, the percentage of the nanomaterials are less, but the strengths of that material will higher. Same material like fly ash, 5% microfillers and 2% nanofillers. So in that condition, if you see the microfillers, when compared to that nanomaterials, the microfillers are giving less strength. The nanomaterials are giving more strength when compared to microfillers with a less percentages. So this is the thing. Finally, I'll conclude here with this. If you have any questions, I'll try to answer. A few questions already had in the chat box, and then I answered it. If anybody have a questions, then you can write in the chat box so that I'll answer that.
So any questions with the participants, they can ask to unmute. I will unmute you. You can raise your hand. Participants can unmute and ask the question. So I think no questions with the participants. Can we make a new tool with titanium base metal?
Can we make a new tool with the titanium base metal? Means like cutting tool, you are saying, like you are pointing about you are saying about the cutting tool, composite. Okay, so yeah, you can make a new tool, but in the cutting tool, exactly. So in a cutting tool, like if you are using a titanium, then you need to see what type of material you are adding it and how much amount of abrasion resistance is there. Like as I said, tribological properties, because when you are cutting it, there will be a more friction will be developed between the cutting tool and the material. And when the friction is there, then because you are using like a composite, it's not a pure metal you are using it. Composite means what type of material we are adding into it and how much amount of tribological resistance for that material, because we need to go for some abrasion, dry sand abrasion, and then it's not about erosion. We don't no need of erosion. Abrasion we need to go it, and we need to see the pin and disc as well as the dry sand abrasion, how this tool behaves when you prepare that composite. So how much wear resistance is there. So because when you are cutting that material, more frictions will develop and due to that wear will take place. So that we need to check when you are fabricating it. Like if you are going for a titanium, we need to see add a ceramics which having a high strength, high hardness. So any more questions related to it?
So last class we discussed regarding your deflection by the integration method. So today we discuss about shall I discuss integration method on your section? Like, this,
Hello.
Hello, ma'am.
Yes, sir. You are waiting for the question. Hello.
this lecture completely is not done on your section. Right?
Hello. Any questions from the participants?
Explain the Raman equation for deflection. These things I explained. But I'm not explaining the Raman integration method.
Hello.
Is it? I think so. I think I explained these things. I'm not sure what the anyone can tell me. Is it Rezi, are you there? See, yeah. Are you here?
Tirupati, sir, you want to talk, sir? I'm unmuting you. You please unmute yourself, sir.
Thank you, madam. Thank you. Madam, myself Tirupati Kadam from CMR IT. And very nice session, sir, madam. My question is, there is a Inconel material, Inconel 625 super alloy. Can we stir cast, sir, for that? Can we do stir casting with Inconel material, and can we add silicon carbide particle in that material, sir?
Hello. Raghavendra, sir.
Yeah, ma'am. The question is about the Inconel material. Yeah, the Inconel material, you need to see the melting point of that material. Based upon the melting point, I think the Inconel also you can melt and you go for stir casting process. Only one thing is like when you are going for a stirring process, like whatever the material which you select, whether it may be Inconel or any other metal, the thing is required is how much amount of like what is the melting point of that particular material.
Mostly an access method is used for your detection program. Why is second method used? I'll tell you. The first I hope is about integration method.
Hello.
Any more questions from the participants? So you have one more question. Okay.
Okay, thank you, madam. Thank you, sir. Thank you, sir.
Participants can unmute themselves straight away and ask the questions, please. So I think there are no questions with the participants anymore. So with this, we come to the end of this session. Hello. Raghavendra, sir.
Ma'am.
Yes, sir. Thank you very much for your time and your valuable information, sir. Actually, this has been an